I'm going to go through the practice test, the FRQ section. Okay, the first part here, we're talking about silver carbonate. And in silver carbonate, we're given the KSP, so that's important. We're probably going to need that. So first is write the dissociation equation for silver carbonate. So we're just saying, what is the equation that goes along with the idea of KSP? And that is silver carbonate solid breaks up into two silver ions and a carbonate ion. So this is an easy question. Then we go on, it says a 0.05 gram sample of silver carbonate is placed in pure water to form a 1 liter solution and a precipitate forms. So what that implies is that if I had a solution, if I was going to make a solution and I put some of my solid in, that not all of it dissolves. Okay, we're going to end up with some solid at the bottom. Okay, so that means that the solution itself is saturated. We can do a calculation with that, but there is some solid at the bottom. So if I had a saturated solution and I wanted to find out what is the concentration of silver, well, we know the way this breaks up, is if S of this breaks up, I'm going to get 2S of my silver, and I'm going to get S of my carbonate. So I want to find out what's the solubility and take 2S, and that'll be my answer. So this is a 2-to-1 compound, so I know it's going to be 2S squared times S. And now I can just solve, so I'm really doing KSP is equal to 4S cubed, solving for S. Okay, so S comes out to be 1.3 times 10 to the negative 4, and the silver ion concentration is double that, so it'll be 2.5 times 10 to the negative 4 molar, and that's the answer. Now, next one says, what's the minimum volume of water that should be added to dissolve all of that precipitate? Well, the useful value we have here is the solubility. Okay, we know that the solubility, how concentrated a solution can I make? And it's just like, any other question we had before is, if I wanted to make a 1.3 times 10 to the minus 4 molar solution and I had 0.05 grams, how much volume would that take? So, let's look at our equation. We're just going to say, start with grams. And then we use the molar mass given at the top, grams to moles. So now we have moles of our solute. And then we're going to use the molarity, the solubility, and we'll go from moles to liters. And we find out that that's 143 milliliters that we need total in order to dissolve the solution. Okay, but we're starting with 1 liter, so we need to add another 0.43 liters or 430 milliliters. So we're going to get the final volume, 1.43 liters, and subtract the 1 liter we began with to figure out how much water add in order to completely dissolve that sample. Now, what's the molar solubility of silver carbonate in a 0.1 molar solution of silver nitrate? So this is a common ion effect problem. We're going to have silver in common. So instead of the idea that KSP equals, solubility squared times solubility, 2S times S, 2S squared times S, we have an initial value of silver, okay, because of the silver nitrate solution. So what we end up with is we have our KSP is equal to 0.1 molar plus 2S, and that quantity squared times S. And that's what's written here in the second step. Now, in order to solve that easily, now if you have a big calculator and you can solve that, go for it. Okay, but we can also assume that that 2S is much smaller than 0.1, and that's going to be a very good assumption. So if that's true, then we can make this equation turn into the KSP 8.1 times 10 to the negative 12 equals 0.1 squared, okay, times S. Okay, so we're just getting rid of that 2S right there because it's really small. It's not going to change our answer very much. And so we're going to divide by 0.1 twice. That's going to be 8.1 times 10 to the minus 10 equals solubility, and that's where this answer is coming from. So we're finding out that the solubility in a solution that already has silver ions will be 8.1 times 10 to the negative 10. Now, we should go back and say, okay, is our assumption correct? Yes. If solubility is 10 to the minus 10, that is much, much, much smaller than 0.1, so that was a good assumption. Now, continue on with this problem. What if we put in some ammonia? Okay, so silver and ammonia. Now, why do we care about ammonia at all? Ammonia, we know sort of looks like a little mutant Mickey Mouse and has three nitrogens, okay, and three hydrogens on a nitrogen, and it's going to have a slightly negative side, it's going to have a slightly positive side. So the silver ion would be surrounded by these ammonias, and that forms what we call a complex ion or a coordination compound, and that does usually affect the solubility. Well, here's some information we have then, and that is if I take silvers and put them with some ammonias, then I will form the silver ammonia complex, and for that there is a Kc of 1.6 times 10 to the 7. Now that's a pretty large number, so actually this reaction does occur. Find the value of Kc for this reaction. Carbonate plus ammonia turns into the ammonium ion and carbonate. Okay, so what's my value for this? Now I can see if I can put together a couple equations to make this equation, I can multiply their k's to get this. So here's 1k. Here's one equation right here, the silver ion. And would I use it as is, or do I need to turn it around, or do I need to double it? And my clue here is this ammonium, it's a silver ammonium complex. And for here, it's in my equation, it's on the correct side, it's on the right side, so I don't need to flip my equation. But I do need two of them, and because I need two, then when I use this value here, I'm going to have to square it. Now, what else do I need? I need something that has silver ions, and I need something that has a silver carbonate. And so I go, okay, wait, way back at the beginning of the question, okay, I had this equation that I've forgotten, and it's fair to use because it's all part of the same question. So this equation, where I have this value, I can use that equation. And if I do look at it, this is on the correct side, so I'm just going to use it as is. I don't need to multiply. Okay, so I don't need to, don't have to adjust this. So here's my KSP value from the beginning, and I'm going to use it as is. Here's the equation from right here, okay, but I'm going to have to square it. So when I get done to get my final equation, by putting those together, and you can see I can put them together, because what's going to happen is I'm going to have silver, two silvers and two silvers, because I'm going to double this. And I think that's all that drops out. Okay, so when I'm done with my equation, then I have a silver carbonate. I've got 4 ammonias, and I'm ending up with 2 of these complexes, and I have 1 carbonate. So I have created this equation from these two, but I had to double this equation in order to make it happen. So my value is going to be the K1 value, okay, times the K2 value squared. And here's the equation, and I end up with 2.1 times 10 to the 3rd. Okay, so I found my value. So the question is, conceptually, does the addition of the ammonia increase, decrease, or have no effect on the solubility? Well, we can see here, this new equation has a value that's greater than 1. Okay, and the greater than 1 means that is going to go forward as you do this reaction. It's going to be product favor. We're going to end up with a lot of these products. Over here. We're going to end up with a fair amount of these products compared to the reactants. So that means if it drives it forward, my silver carbonate would dissolve better if I put the ammonia in. So that means it's going to increase my solubility, and that's because my K, this K here, is greater than 1. It's going to be product favored. I'm going to get my carbonate to dissolve. Okay, second question. Here we have an equation, okay, and we can see what's going on. Here's a gas, here's a gas, here's a gas, and heat on the right. We may need that. At a particular temperature, the Kp is 15. So here's a reaction mixture. Here's the values for each of my things. Okay, this sounds like we're going to do a Q. And so let's write the equilibrium constant expression. Okay, so that's partial pressure of the SO2Cl2 times the partial pressure of SO2 over the partial pressure of SO3 and SCl2. So just like we've done in class. And that has a value of 15. We're just copying that down from the problem. Now again, if you do this, if this says write the equilibrium expression, okay, be sure and include the Kp equals. I've seen some people where all they do is put this section in and they don't get credit. Okay, for part B, determine whether the reaction mixture is at equilibrium or which direction will it shift. Well, they just gave us all these values here. So if we substitute those values into the expression, then we are making our Q, okay? And if we do that, just put in, 1 and 1 divided by 0.25 and 0.5, everything to the first power, we get a value of 8. Well, the K for this is 15, and this is 8, which means we need to get it larger, which means we need more products. So if Q is less than the K, the reaction is going to shift to the right, okay? And that's the answer. It is not at equilibrium, and it will shift to the right in order to reach equilibrium. Okay, what's the value for the Kc? What's the value for the Kc? Well, let's go back and look here. We're going to do, delta N. So here's 1 mole of a gas, 1 mole of a gas. Here's 1 mole of a gas, 1 mole of a gas. So it's going to be 2 minus 2. The delta N is equal to 0. And that's a good special case. So let's go back here. So remember what we say is that the equation is Kp equals Kc times R times T delta N. But if delta N is 0, that makes this whole thing turn into 1. So the Kp and the Kc are the same. So exactly here, that since the delta N is 0, these have the same value. So what's the value of the Kc? It's 15. Now something else to notice is that if you were to talk about what the units were, we don't bother with units on these, but if we did, we could see that, this would be atmospheres, atmospheres over atmospheres, atmospheres, to be unitless. So in the case where the Kp and the Kc are the same, it's because all the units have canceled out. Now the last part here, if the temperature is raised, will the value for Kp increase, decrease, or remain the same? Now the way I always think about this is if I have an equation here, like I have here, and I say, okay, I'm going to increase the temperature. Okay, so now I have too much heat, so I'm going to shift the reaction back to the left. Well, if I want to know what happens to my K, I always just look at what the products are doing. Whatever change the product does, that's the value, that's how the change of K is going to be, because K is products over reactants. So if my SO2 got larger, then I would have, greater number for my products over my reactants. Or in this case, this is getting smaller. So that means my numerator gets smaller and my denominator gets greater. So if this is going to shift to the left and this SO2 is going to get smaller, my K value is going to get smaller as well. And right here, so what's going to happen to your K when the temperature is raised? The reaction will shift to the left. Okay, so K must have decreased. And another way to look at that is, Q is greater than K. For the moment, Q is equal to K at equilibrium. But now it's shifting to the left, which means Q must be greater than K to make it shift to the left. And that's the FRQ.